Introduction. Capacitance is a fundamental property of electrical systems that describes a capacitor's ability to store electric charge. In a parallel plate capacitor, capacitance depends on the area of the plates, the distance between them, and the material placed between the plates. The purpose of this lab was to measure the capacitance of a parallel plate capacitor using a multimeter and compare experimental results to theoretical values. Materials: parallel plate capacitor, multimeter, cardboard, dielectric ruler. Table 1 and 2 area 0.0243 meters squared. Dielectric constant in vacuum 8.854 times 10 to the negative 12. Systematic error 6.0 times 10 to the negative 12. Plate separation 1 millimeter, 3 millimeters, 7 millimeters, 11 millimeters, 17 millimeters, 21 millimeters, and 30 millimeters. Theoretical capacitance 2.15 times 10 to the negative 10. 7.18 times 10 to the negative 11, 3.1 times 10 to the negative 11, 1.95 times 10 to the negative 11, 1.26 times 10 to the negative 11, 1.02 times 10 to the negative 11, 7.18 times 10 to the negative 12.
Does the other side have a knob?
Just be this value that we have right
here. Procedure Step 1. The systematic error of the multimeter was measured by separating the plates as far as possible and recording the reading. Theoretical capacitances were calculated for plate separations of 1 millimeter, 3 millimeters, 7 millimeters, 11 millimeters, 17 millimeters, 21 millimeters, and 30 millimeters. Capacitance was measured at each distance and corrected by subtracting systematic errors. Then the percent error was calculated.
192 times times 10 to the 11, negative 11.
37. 0.037.
No, 35.
We were at 17 before, right?
Yeah. Procedure Step 2. Place the dielectric plate between the parallel plates, then bring the parallel plates as close together as possible. Measure the values and correct them by subtracting the systematic error on the multimeter. Then repeat, but now use the cardboard plate.
Go back again. This is step 2 of our experiment. We're placing this as a dielectric, and then we are bringing these as close together as we can. I mean, this gets still so good. That one. It's gonna be
1, 5. Procedure Step 3. Place both the cardboard and dielectric plate together between the two plates and bring them close together. 1. Will the equivalent capacitance be greater or smaller than the dielectric one? The equivalent capacitance will be greater than dielectric one. 2. Will the equivalent capacitance be greater or smaller than the dielectric 2? The equivalent capacitance will be smaller than dielectric 2. 3. Does having a dielectric will increase or decrease your percent error? Why? Adding a dielectric would decrease the percent error because larger capacitance values are easier for the multimeter to measure accurately.
I gotta fill in some space, man. Gotta keep that.
Stage fright, bro.
Are you?
The red. So where does
Go slide it.
This
No slide.
This is for
That?
okay.
Data analysis. We compared our measured capacitance values to the theoretical values from the parallel plate capacitor equation. After subtracting the multimeter's systematic error, we saw the expected trend. As plate separation increased, the capacitance decreased. Our percent error was highest at the smallest distance, but it became much smaller at most larger separations, showing our corrected measurements matched the theoretical model more closely. Conclusion. In conclusion, this experiment confirmed that capacitance is inversely proportional to the distance between the plates of a parallel plate capacitor. As the separation increased, the capacitance decreased, which matched the theoretical equation. The insertion of dielectric materials increased the capacitance, demonstrating how dielectrics enhance a capacitor's ability to store charge. When two dielectrics were combined, the equivalent capacitance behaved as expected for capacitors connected in series, and the theoretical method using calculated dielectric constants produced the lowest percent error. Conclusion question. Reflecting on your predictions and thoughts in step 3, are these results what you expected? Why or why not? Yes, our results were mostly what we expected. We expected capacitance to decrease when the distance increased, and that is what our corrected data showed. We also expected dielectrics to increase capacitance, and our measurements increased when we inserted dielectric materials. If anything was surprising, it was that the percent error was much higher at the smallest separation, which we think happened because small distances make the setup more sensitive to spacing and measurement uncertainty.